All right, next up, we're going to talk about bond polarity, not to be confused with molecular polarity. We'll learn about that later. So just determining if a covalent bond is polar or nonpolar. So again, this term is specific for covalent bonds. Sometimes two atoms share electrons equally. If there's an equal sharing of electrons between the bonded atoms, we call that a nonpolar covalent bond. This will happen when the bonded atoms are identical, such as the case as in the diatomic molecules. We can also have nonpolar bonds between different nonmetal atoms. Whether a bond is polar or nonpolar, whether the atoms bonded together share the electrons equally or unequally, depends on their electronegativities and, more appropriately, the difference in their electronegativities. So if the difference in the electronegativity of the bonded atoms is really small, now you don't have to know this number, but technically if the difference in electronegativity is less than 0.3, then we would consider that bond to be nonpolar. So certainly going to see this when we have the diatomic molecules. If you have two chlorine atoms bonded to each other, the difference in their electronegativities is 0. So remember, what is electronegativity? The ability of an atom, when it's bonded to another atom, to attract electrons. So which nucleus, the chlorine or the chlorine, is pulling harder on these shared electrons? The answer is they're pulling the same. And so because they're pulling the same, those shared electrons are going to spend their time right in the middle of those two atoms' nuclei. And therefore, we don't have a bond that has opposite ends. This is a nonpolar covalent bond. So if you're with me in Chem 1, I use the analogy of tug of war. You have two equally matched teams pulling on the rope. The flag in the middle of the rope stays right in the middle. Here you got two evenly matched atoms. They're pulling on those shared electrons equally. And so those shared electrons spend their time right in the middle of those two nuclei. All right, polar bonds. So the word polar means opposite ends. So a polar covalent bond occurs when two atoms have an unequal sharing of electrons. This occurs when the bonded atoms are different. This occurs when the bonded atoms have different electronegativities. The electrons in the bond will shift away from the less electronegative atom and towards the more electronegative atom. Let me show you an example. Which is more electronegative, hydrogen or chlorine? Well, chlorine is one of the most electronegative elements, so chlorine is more electronegative than hydrogen. So what does that mean? That means that the chlorine is able to pull the shared electrons away from hydrogen, not completely away. So it's not like we're forming a cation and anion as we saw in the case of ionic bonding. So it pulls the electrons a little bit away from the hydrogen, more towards chlorine's own nucleus. And so there's an uneven or unequal sharing of electrons. So going back to the tug of war analogy, let's say that you have one team that's a little bit stronger than the other team. The flag that's on the rope will move closer to the stronger team. Same thing here. Those shared electrons are going to spend more time closer to chlorine's nucleus than they are hydrogen's nucleus. We end up with a bond that has opposite ends. One end of the bond is partially positive, and one end of the bond is partially negative. So we can show that with a couple different symbols. So one of the symbols we can use is lowercase delta negative or delta positive. Kind of a squirrely looking D, kind of an S type thing. You can see that in your notes there. So that's one way we can show which end of a bond is partially positive. So we're talking about partial charges, not total negative and positive charge, or which end of the bond is partially positive. We can also use arrows, so an arrow with the head pointing towards the more electronegative end and a crosstail on the more positive end. So let's go back to our example of HCl. So let's use both systems. I'll start with the arrow because I have not a lot of room there. So again, arrow pointing towards the more electronegative atom using the deltas. The chlorine end is partially positive, and again, we can put it next to the Cl and next to the H. I just put it above them. The chlorine end of that bond is partially negative, and because of that, then the hydrogen is partially positive. The separation of charge in a polar covalent bond creates something called an electric dipole or dipole moment. So we'll get to that term in just a second. I'll have you fill that out in the notes. Take a look on page 277, figure, or rather example 710. So we have some different bonds to look at: fluorine, 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 chlorine, fluorine, bromine, chlorine, bromine, and so on. And so whether a bond is polar and how polar it is depends on the difference in electronegativity. So if you look at the bottom of the solution, and let's go all the way to the right. Let's look at the fluorine-fluorine bond. So the colors represent electron distribution. We have all green there. That means that is an area of low electron distribution. So those fluorine atoms are sharing the electrons equally. We see that, again, the size of the lobe, if you will, also represents the distribution of electrons. And so the electrons are equally distributed among the two fluorine atoms. Same thing we see with chlorine. A bond between chlorine and bromine is ever so slightly polar. Again, look at that difference in electronegativity, just 0.2. Technically, based on what I told you earlier, that would be a non-polar covalent bond, even though we have different nonmetal atoms. Cl and I, difference in electronegativity is 0.5, so it's a little bit more polar. And then we see FCl, more polar, FBr, even more polar. And so again, where the electrons are spending most of their time, or if we have a region of high electron distribution, that's shown in red versus in green. So red is partially negative, green is partially positive. Alrighty, go ahead and turn to page 284. Question or exercise number 74. It wants you to indicate whether each of those bonds is polar or non-polar. And if it is polar, to use the delta, positive, delta, negative, to indicate which side of the bond is partially positive and which side of the bond is partially negative. Usually the general trend in electronegativity works, but in case it doesn't work, and it may not work in some situations, the table of electronegativities is on page 232 in your textbook. Use that. Determine the difference in electronegativity. Again, we'll say if it's less than 0.3, it's more non-polar than it is polar. And more than 0.3 difference, it's definitely going to be polar. All right, go ahead and pause the video and work on that one. So here's what we got to underline the more polar of the bonds. So in the first one, oxygen is more electronegative than nitrogen. You can use the trend, or you can use the table in the book, and that'll show you that it is true. And so the difference in electronegativity of carbon and oxygen is greater than the difference in electronegativity of carbon and nitrogen. So oxygen being more electronegative than carbon, delta negative for oxygen, delta positive for carbon. The next two, actually, those bonds are both nonpolar. The difference in electronegativity is 0. So both nitrogen and chlorine have the same electronegativity. Both carbon and sulfur have the same electronegativity. No way to really know that unless you are using the textbook and the values for electronegativity. pH versus Pn. pH, I believe, is nonpolar. Both phosphorus and hydrogen have an electronegativity of 2.1. So Pn is more polar, nitrogen being more polar, nitrogen having a higher electronegativity than phosphorus, so delta negative for the nitrogen end. Then lastly, Bi, the bond between boron and iodine, is more polar than the bond between boron and hydrogen. The bond between boron and hydrogen, that difference in electronegativity is 0.1. We would classify that as nonpolar. All right, I mentioned this word before, dipole moment. Dipole moment really is a way of quantifying the polarity of a bond or a molecule. Here's the definition: the product of the distance between the charges and the magnitude of the charge. Go ahead and take a look on page 277 again. So take a look at the relationship between the difference in electronegativity, delta En, it says in the table, and the dipole moment, or that quantified way of expressing the polarity of a bond. The HF bond is the most polar. The difference in electronegativity is the greatest amongst those in the table there, and therefore has the highest dipole moment. Notice for the hydrogen-hydrogen bond, the difference in electronegativity is 0, and the dipole moment is 0. That is a nonpolar bond. So again, if you see that term dipole moment, it just refers to the polarity of a bond or molecule. For all intents and purposes, there's no such bond that is pure ionic, no such bond that is pure covalent. Says all ionic bonds have at least a small amount of covalent character where the atoms are kind of sharing the electrons a little bit. And all covalent bonds have at least a small amount of ionic character where, again, if there's a big difference in electronegativity, that more electronegative atom is really pulling away on those shared electrons and maybe even in some cases forming some ions. So again, here's how it works. The bigger the difference in electronegativity, the more ionic the character of that bond, and the less covalent. The opposite is also true. The smaller the difference in electronegativity, the more covalent that bond, and the less ionic. So again, referring to that table on 277, the HF bond is the most ionic. The difference in electronegativity is pretty big. And the HH bond is the most covalent or least ionic. All right, that concludes this video. I'll stop here, and the second part of this lesson will be the beginning of VSEPR theory. So take a look there.